All right, class, welcome to section 6.3, logarithmic functions and their graphs. So let's look one more time at what an exponential function looks like. So here it is. We graphed these last time, but I do want to remind you, if I were to plot some points, which we also found plenty of times last time. So here's an x and here is the y. If I plug in, let's just take a few points. 2 to the 0 we know is 1. 2 to the 1 is 2. 2 squared is 4. 1/2 and 1/4. So I've plotted this for you. 0, 1, 1, 2, 2, 4. Then -1. Oops, what was that? -1, 1/2, 1/4. So of course, this graph very nicely is going to, as you see, have a domain that's all real numbers, a range that is 0, infinity, and it has a horizontal asymptote at y equals to 0. So all features that we discussed in the last section. Okay, now, as you notice, this function is 1-to-1. Is 1-to-1 because it does pass the horizontal line test. Every horizontal line you draw through will cross this graph only one time. So therefore, it must have an inverse. So we discussed very recently in 6.1 that only 1-to-1 functions have an inverse. So if you have a 1-to-1 function, it's going to have an inverse. In other words, one that undoes it. So how do we find that inverse? Let's find it. Okay. Well, we said we call f of x by y. So here it is. It already has the y at the front. Then the second step we learned was that we're going to replace x with y and y with x. In other words, we're going to swap x's and y's. And then we have to try and solve for y. So whatever you try to do is just not going to work from what you can divide, as this is not a multiplication. You can't square root it, as this is not a square. It's a y power, so you can y root it, but then it would definitely just put the y on top of the x. So in other words, if you try to write the yth root of y, yes, it will go away from here, but then you still have the y right here as a root to the x. So it's not really gone. Okay. So let's try this again. X equals to 2 to the y. So no operation that we have performed so far this semester can solve for y. So there's a new operation that you don't know about, and that is that y is equal to log with base 2 of x. So we read this as log or logarithm, but we get lazy and we just say log with base 2 of x. So that is the inverse function of the exponential function. Now, one thing that I want you to notice is that the base of the exponential function is the same as the base of the logarithmic function, okay? And then, as we'll see in a bit, we're just going to swap the x's and y's, right? So it is important to understand what a logarithm is. A logarithm is the exponent to which we have to raise the base in order to get the number inside. So anytime I'm writing a log with whatever base b I have of x, this is going to equal to the exponent to which we have to raise the base b in order to get x. So here it is, this logarithm with base 2 of x, this y, is coming from here. And what was y? Y was the exponent to which we had to raise 2 in order to get x. So let's try and let that idea sink in by evaluating some logarithms. So in other words, what would be log with base 2 of 8? So again, what I'm thinking is, what is the exponent to which we have to raise 2, the base 2, in order to get 8? So that exponent has to be 3. So again, a logarithm will always equal to an exponent. It solves for an exponent. Anytime we're going to be missing an exponent and want to solve for it, we're using a log. If I want to find a log, that means I need to find a certain exponent. So let's try this again. What is log with base 5 of 25? Okay. So what exponent do I have to raise 5 to in order to get 25? And that is 2, because 5 squared equals to 25. What is log with base 4 of 16? So what exponent do you have to raise 4 to in order to get 16? That's also 2, because 4 squared equals to 16. Now again, exponents can be anything. So for example, what would be log with base 3 of 1/3? In other words, what exponent do I have to raise 3 to in order to make it a 1/3? And then we've just been reviewing exponents, and that is a negative exponent. So negative exponents give us fractions. So therefore, what would be log with base 2 of 1/4? So what exponent do I have to raise 2 to in order to get 1/4? Well, it's a negative because I'm getting a fraction, and it's a negative 2, so 2 to the negative 2 equals to 1/4. Okay. So hopefully this is starting to sink in. So what kind of exponent do I need to raise 7 to in order to get 1? Now, if you remember, 0 is the one exponent that if I raise anything to, I'm going to get a 1. So any number raised to the power of 0 equals to 1. So that's how it works. Now, if you look on your calculators, you're just going to see a log, but you're not going to see a base. So yes, somehow we will learn how to use these buttons, actually both of them, the LOG and the LM buttons, to find logs, but not just yet. Okay. And so here, let me give you another one. Exponents don't have to be integers, so they don't just have to be positive, negative, whole numbers. The exponents can be decimals as well. So if you think about what do you have to do to 9 to make it a 3, and I don't mean subtract 6 or divide by 3, but what kind of power do you have to raise 9 to in order to get 3? That power is 1/2, because a 1/2 exponent, again, means a square root of 9, and that's what equals to 3. So again, answers can be positive, negative. So remember, logarithm is an exponent, and as we discussed in the last section, exponents can be any real number. They can be positive, negative, whole number, decimals, anything. Okay. All right. So let's keep playing with this idea that a fact that a logarithm undoes an exponent. And so let's switch from logarithmic form to exponential form and back. Okay, so I'm going to start with something familiar. 2 to the power of 3 is equal to 8. We all know that, right? Now, what would be the logarithmic form to this? So, logarithm with the same base. So the good news is the bases are going to stay the same. So logarithm with base 2, and then you just swap the numbers around the equal. So of 8 equals 3. So what exponent do you have to raise 2 to in order to get 8? That is 3, because 2 to the third is equal to 8. Yes, and I did write this for you right up above. But I want to show you how they mean one and the same thing, just in different formats, right? Same as writing the square root of 9 is 3 is the equivalent in inverse form that 3 squared equals to 9. Yes, so that's the equivalent of squaring versus square rooting, raising a number to some exponent versus finding that exponent. All right, so let's try this again. If 3 to the power of x is equal to 81, what would be the logarithmic form of this? Log with base, same 3, and now just swap the 81 and the x across the equal. So log with base 3 of 81 equals to x. Remember, a logarithm always has to equal to the exponent. The logarithm ends up equaling to the exponent. So let's try this again. If a to the b equals to c, what would be the logarithmic form of this? Log with what base? The same base as the exponential has it, of a. Log with base a of c equals to b. So, of course, it makes sense when we have numbers because these are familiar values. But this is what I'm trying to show you, how to switch from an exponential form to a logarithmic form, even if you are not given numbers. So the idea is, because this is how we'll solve exponential equations. So right here is an exponential equation. I do not have the exponent. Therefore, that's an exponential equation. So how do I solve for this exponent? I'm switching it into a log. And now I just have to figure out with my calculator what is log with base 3 of 81. So let's go backwards. And here it is. Log with base, let's say, 4 of 1 over 16 equals to negative 2. What would be the exponential form to this? Well, again, you keep the same base. 4 to the power of negative 2 equals to 1 over 16. Okay, and that's true. 4 to the negative 2 equals to 1 over 16. Log with base 5 of x equals to 3. This, by the way, is a logarithmic equation. You see how I'm missing an x, and that x is inside the log. So what we're going to do is we're going to switch it into exponential form. And what is its exponential form? 5, the same base. And now swap these around to the power of 3 equals to x. And by the way, 5 to the 3 would be 125. So there we solve for x. Here one more. Log with base b of 2 equals to a. What would be the exponential form to this? The base b to the power of a equals back to 2. So we do this. B to the power of a equals to 2. All right, so hopefully this starts sinking in, as in how do we use logs in connection with exponents. We are going to see how we can find logs with our calculator. But for now, I'd like to graph and think about everything. I don't know why this keeps popping in. And think about anything has to do with logarithmic functions. So we're going to graph logarithmic functions. We're going to also graph them using transformations. But for now, a logarithmic function with base b looks like this. Okay, so we read this as log or logarithm with base b of x. Now remember, a logarithmic function is the inverse of an exponential function. And as such, it has to have the same rule. So the base has to be a positive number not equal to 1. Okay. There will be some rules about the domain and the range of any logarithmic function. But before we go there, let's graph a logarithmic function. And of course, the easiest one that we could graph is log with base 2 of x. So let me plot some values here. Now it is quite difficult to come up with exact values, especially since we've barely started thinking about what a log is. And I want to bring back something we learned in 6.1. And what we learned in 6.1 is this. Now, first of all, this function is the inverse of this exponential function, 2 to the power of x. That's how we found it, right? We wanted to find the inverse of 2 to the power of x, and we came up with log with base 2 of x. So they're inverses of each other, okay? As long as you keep the bases the same, a log and an exponential function are inverses of each other. Now, what did I say? I said that a function and its inverse, we learned this in 6.1, swap x's and y's. So here it is. It is really easy to come up with a whole bunch of points, which I actually already did for you on page 1, of points that would be necessary for us to graph the function 2 to the x. Okay. Now, because a function and its inverse swap x and y, that's exactly what I'm going to do. I'm going to take these two columns and swap them. So instead of 0, 1, I have 1, 0, 2, 1, 4, 2, 1 half, negative 1, and 1/4, negative 2. Okay. And now let me plot these points. 1, 0, 2, 1, 4, 2, a half with negative 1, a quarter with negative 2, so here it is. And hopefully this makes a lot of sense. As we already know, a function and its inverse are symmetrical about the y equals to x line. I'm going to try and go back here. So all I'm doing is I'm taking the exponential function and I'm flipping it over the y equals to x line. And then it's just sideways, kind of like we took a square, an x squared, and put it sideways to make it a square root, and so on and so on. Now, as you see, based on this graph, the domain is super important for a logarithmic function because the domain is 0 to infinity. This graph exists only to the right of the y-axis. The range, however, is all real numbers, which absolutely makes a lot of sense because remember what I also taught you in 6.1, that a function and its inverse swap domain and ranges. So this is now the new range of the logarithmic function, and this would be its domain. Okay. Now, not only that, every exponential function had a horizontal asymptote at y equals to 0. Now that we put this one sideways, the logarithmic functions, all of them will have vertical asymptotes at x equals to 0. So in every single sense, a function and its inverse swap x's and y's. Y equals to 0 was a horizontal asymptote. Now x equals to 0 is a vertical asymptote, as you see. Okay. They swap domain and ranges because they swap x's and y's. So this is what the graph of any logarithmic function is going to look like. So in general, let me draw this again one more time. And I'm going to show you in general, if you are looking at a logarithmic function with base b, I'm going to say this: if b is a base that's more than 1, we take the 2 to the x, 3 to the x, and we put it sideways. They all are going to cross, same as every exponential function crosses through 0, 1. They all cross through 1, 0. Okay, so this is what a logarithmic function looks like that has a base that is more than 1. Now, if the base, same as with the exponentials, is a number between 0 and 1, remember the base has to be positive, it's still going to cross through 1, 0, but it's going to be flipped this way. So it's really one of those 1/2 to the power of x functions that get flipped. So the base is more than 1, then the graph is increases. If the base is less than 1, then the graph is decreasing. Again, they all cross through the point of coordinates 1, 0. They all will have a domain that's only positive values, and they will all have a range that's all real numbers, and they will all have a vertical asymptote that is the y-axis, aka x equals to 0. So extremely important, only positive numbers can be plugged into a logarithmic function. So therefore, the logarithmic functions, again, will have restrictions on the domain, same as the square root function. You can only put positive numbers inside a square root function, but you could also put a 0 inside a square root. You can't even put a 0 inside a log. So here I'll show you. So you don't know yet how to use these logs, but here I'm plugging in 0. It says calculator error domain. You can't have that. Okay, let's plug in a negative. Nope, no real answer. Calculator error, no. Okay, fine. Let's plug in a positive number. Okay, well, there's an answer. So you can plug in zeros, you can plug in negatives. Okay. So here it is. Graph. State the domain and the range and the equation of the vertical asymptote. First things first, I want to show you how to find the domain on paper. We could do that with the graph. But to find the domain of a logarithmic function is very important. So what we do is we take this x minus 1 value that's inside the log and we say this has to be strictly positive. So therefore x has to be strictly greater than 1. So therefore the domain, I'll write it above, is 1 to infinity. So this graph, you will only find it to the right of 1. Okay. Now, we're not going to find domain, range, and so on paper, but this is going to be important. Sometimes we only need to find the domain and not necessarily have to graph the whole function. but just look at the domain, and that's how you could easily find it. Put whatever's inside the log to be more than 0. That's the rule on logs. Okay, now, let's see. Let's graph it. So I'm going to use transformation. So the first thing I'm going to want to graph is the log with base 3 of x. Again, you can come up with a few points. Remember, you can also take the 3 to the power of x, find the points for that, and swap them like we did to 2 to the power of x. But here I'll just put values in. Log with base 3 of 1, remember, is 0. They all go through 1, 0. Log with base 3 of 3 is 1. So instead of 2, 1, I have 3, 1. The next one up here would be 9, 2. Log with base 3 of 9 is 2. Log with base 3 of 1/3 is -1. So it is very similar to log with base 2 of x. Same as 2 to the x versus 3 to the x. The graph just gets closer to the axes. Okay. And then we have a couple transformations. And my transformations are, number 1 is go to the right. So graph log with base 3 of x minus 1. That simply means to take all these points and move them 1 unit to the right. Now, what else is moving 1 unit to the right alongside with it is our vertical asymptote. So before we had to be all to the right of 0, now we have to be all to the right of 1. By the way, that's also clear from the domain of the function. You have to graph this only to the right of 1. And then plus 2, as we've done so many times now, we would simply shift this graph 2 units up. So the vertical asymptote stays where it's at. The graph very slowly but surely keeps increasing. So again, the domain, we already figured it out on paper, but I'll write it again because now we even see it from the picture. The graph is all to the right of 1. The range is all real numbers, and the vertical asymptote we have is x equals to 1. That's the vertical asymptote. Okay. And here's another one. Again, you don't have to find the domain on paper. We're going to do that actually in a bit, as I said. We're looking at finding domain sometimes without actually doing the whole graphing. So let's do the whole graphing here first and then see if we can read the domain. And if that makes sense based on what we can find on paper. So first things first, start with a basic logarithmic function. So log with base 2 of x, again, might be a little bit harder to come up with these values. Again, you can plug in 0, but you can plug in a 1. Log with base 2 of 1 is 0. 2, log with base 2 of 2 is 1. Again, the power to which you have to raise 2 to in order to get 2 is 1. I've also had these points up above for you, by the way. So this should be enough for me to know how the graph goes. They all go through 1, 0, 2, 1. The next one would actually be 4, 2. 1/2, -1. So here's the graph. I've graphed it for you up above. So it's the same shape, it just doesn't go up. It doesn't flatten out as much as the log with base 3 of x. All right, so the next function over, what kind of transformations do I have here? I have a log with base 2 of x plus 2. So the x plus 2 means I have to shift 2 units to the left, the opposite direction. So I'm taking all these points and I'm moving them 2 units to the left. So alongside with it, whatever else is moving is the vertical asymptote. So x equals to 0, now moving those x's 2 units to the left, x equals to -2 will be my new vertical asymptote. Okay, and the last transformation here is to take this log function that I had and multiply it to -2. So what that does is take all the y's and multiply them by -2. Okay. So here's a y coordinate. That's 0. I'll multiply by -2. It stays a 0. This y coordinate here bubbled in, as you see, is 1. Multiply by -2, so I'll go down to -2. This is a 2. Multiply by -2 goes to -4. This y value here is a -1. Multiply by -2, and it will go to +2. So what this does is, of course, it stretches the graph vertically by a factor of 2, but it also flips it about the x-axis. So this is my new graph. Now, as you see, the domain is all to the right of -2. The range goes all the way up and down, and the vertical asymptote is, of course, x equals to -2. It stays the same even if we flip this graph about the x-axis. So here I have my vertical asymptote. The graph pushes all the way to x equals to -2. So as I said, I'm going to take a look back and see, does this domain make sense? Yes. X plus 2 has to be more than 0. Therefore, x has to be more than -2, so to the right of -2. So whether you look at the graph and you keep track of all the transformations nicely and you carefully plot in these points and make a pretty graph, not just some wibbly wobbly that crosses everywhere, but these are nice looking graphs. We bubbled in some points, we moved them the correct way, and here's our pretty answer. Okay, so we're pretty much done with this section. I just want to find a couple more things. It's just find the domain. Just practice on this piece of the puzzle, finding domains of functions. Now again, remember, for a logarithmic function, our rule says that whatever's inside the log has to be greater than 0. Remember, with square roots, we said whatever's inside a square root had to be greater than or equal to 0. Now, the logs cannot have a 0 inside. I put it in the calculator and I showed you that doesn't work. So strictly positive values, yes. So it cannot even equal to 0. It's not going to cross or touch the 0. It stays to the right of it. Oops, I've been saying 0 so many times. So I'm adding 3, yes. Then dividing by 3. So x has to be greater than 1. So greater than 1 means anywhere from 1 to infinity. (15 minus 3x is more than 0. I'm going to minus 15 over. So -3x is greater than negative 15. If you remember, we solved all these inequalities, linear inequalities, back in chapter 2. And also what we learned there is whenever you divide an inequality by a negative number, what happens is that the inequality sign reverses. So x now has to be less than positive 5. So less than 5 means all the way up to 5. So negative infinity up to 5. Now, of course, you could graph these and look at what happens, except for you don't know yet how to put in a logarithm in your calculator. You still have to hold on. Okay, this one's super tricky because whatever's inside the log is not going to produce a linear inequality. So whatever's inside the log has to be more than 0. Okay, that's what we've been doing over and over again. So this whole chunk has to be more than 0. Now, this is not a linear inequality. I can't just remove and flip things around and separate the one and only x because x shows up everywhere and it has all sorts of powers. However, luckily, we did cover these kind of inequalities very recently in section 5.4. So this is what we would call a polynomial inequality. So what we want to do is we want to factor it if we can. And of course we can. There's an x greatest common factor. And then I'm going to factor this trinomial some more. So here numbers that multiply to 6 and subtract to be 5 are negative 6 and positive 1. So hopefully this looks even more like a polynomial inequality for you. Again, we recently did that. And the way we solve these inequalities is by graphing. So one of the zeros is 0. Another one is 6. And another one is negative 1. Now this being a cubic polynomial means it comes from here, crosses, crosses back, crosses, crosses up. Okay. So polynomial inequalities, good thing we're covering this after all the stuff we've learned on polynomials. So we want this inequality to be more than 0. So these y values, we want them to be positive. And which piece of the graph fits on the positive side of the x-axis? Well, in between negative 1 and 0. And then again, from 6 to infinity. So here's our answer. Okay. So which x's make this whole quantity, call it y if you want, more than 0. And there it is. All right, so we have two very fancy logarithmic function. One is called the natural logarithmic function, and this is just the inverse of the natural exponential function we discussed in the last section. And so the inverse of the natural exponential function, the natural exponential function was e to the power of x. Its inverse function is log with base e of x, right? So again, we keep the bases the same. And log with base e has another name or another symbol to it, and we say ln. So anytime you see an ln button or the words ln, it stands for the natural logarithmic function, and it means specifically log with base e. So let me show it to you on the graph right here, ln. And just to remind you, as you see, it's right next to an e to the x. These are inverse functions of each other. So ln specifically means log with base e of x. Okay. And then we have another one, the common logarithmic function. We don't have such a thing as the common exponential function. Well, maybe it is, it's just no one uses it. So the common logarithmic function is simply the inverse of the exponential function with base 10. So its inverse is log with base 10 of x. And just this is as common as a square root. So because the most common root is the square root, we stopped writing the 2. But we already know it's a 2 there. So the same way here, the most common logarithm is the log with base 10. So we stopped writing the base. There's no base written here. So if no base is written, same as with a square root, again, it doesn't mean a log with base 2. It actually means a log with base 10. But it's so common that we just stopped writing the base. So to remind you, here it is. Log with no base means specifically log with base 10. And to remind you, see how there's a 10 to the power of x on the same button. So that's the base, log with base 10. So to verify this, you can put in your calculator what is supposed to be log with base 10 of 10. Log with base 10 of 10 is supposed to equal to 1 because 10 to the power of 1 equals to 10. So here it is. Let's test it. What's log of 10? And again, I did not write a base, right? So only if the base is 10, the answer is going to come up to be 1. And there it is. The base is 10, right? So a log with base 10, we don't write the base. Now, finally, those are the only 2 buttons on our calculator. So the change of base formula can be used to evaluate a logarithm with any base with our calculators, okay? So if you want to find the log with some kind of base b of some number, you can switch it to a new base n, let's say, of that number divided by the log of that same new base of the old base. Now, of course, the only 2 bases that we would want to switch things to is the ones that we have on our calculator. So either a base e, so the natural log, or a common base, in other words, a base 10. So let's test it. Remember how I asked you the first question, what is log with base 2 of 8? And of course, the answer should be 3. Now, if you didn't know it, how can you find it? It says you take your calculator and type in ln of 8 divided by ln of the number on the bottom, which is our old base, 2. So let's test it. So what's ln of 8? See how it opens a parenthesis so you know to close it and say that's all I want inside my log, divided by natural log of 2. And the answer is 3. And that's the answer. Now, all the same, we can either grab the natural log button or we can grab the common log button. It doesn't matter which one, as long as you grab the same one both times. So here it is. What's the common log of 8 divided by the common log of 2? 3. Okay, so either way you want to do that. Now, and again, you can go back and find any log of any base. All of these ones that I gave you up above, and I said, can you think a little bit and give me some answers? You can take them all and put them in your calculator and see if you can get the same answers. But of course, mostly, what we want to find, use logs for, it's not like same as, sure, I can put the square root of 9 in my calculator, but I still already know without a calculator that the answer is 3. Yes, or fine. You don't know it, you put it in a calculator, no problem. However, I absolutely do not know what the square root of 23 is. Fine, of 25, yes. But 23 is not a perfect square. I know my answer is going to be about a 5, right? But only a calculator will be able to tell me exactly. So the same thing here. If I want to find log with base 2 of 20, or of 5, or of 3, even just as easy as 3, I have no idea. 2 to the power of 1 is 2. 2 to the power of 2 is 4. I know my answer is going to be somewhere between 1 and 2, but what is it exactly? Let's find out. It's not be a half, I'll tell you that much. ln of 3 divided by ln of 2. It's going to be close, but it's not exactly a half. It's 1.58. I want to find what's log with base 2 of 20. Okay. ln of 20 divided by ln of 2. There you go. 4.32 something. Yes. So now this is now how I can graph logarithmic functions. Again, the only two buttons I can type in are log and ln. Yes. So if I wanted to graph log with base 2 of x, I can't. I have to type in ln of x divided by ln of 2. So that's using the change of base formula to what log with base 2 of x is. So here it is. ln of x divided by ln of 2. And here's the graph. All right, well, that's a logarithmic function. We've graphed them before. Here it is. As you see, the graph is to the right of 0 all the way. Yes, it stays to the right of 0. It crosses through 0, 1. As I've shown you, it crosses through 2, 1. About, well, kind of hard. It crosses through, yes, 1, 0, 2, 1, 4, 2, and so on and so on. So I've put those points in for you. Okay, 8, 3. These are points that I had in the table of values for you. Okay, so if you want to graph log with base 3 of x, sure, no problem. I'd have to put ln of x, or either common log or natural log. It doesn't matter which one you use. By the way, here, let me show you common log of x divided by common log of 2. It's the same exact thing. There is no second graph. It falls exactly on top of the first one because it equals to the same thing, log with base 2 of x. Okay, so here I wanted to do log with base 3 of x. So that's common log of x divided by common log of 3. So as I said, these kind of graphs are going to get closer to the axes as we increase the base. Okay, so there it is. Okay, and that's the end of our section.